would you describe that? Up, up. All right, great. Okay, we're going to swing in the back to Hiram. What does that look like? It's drawn a U, so what would we call that? Up, up. Good job. We'll come up. You have to remind me your name. Megan. What is D going to look like?
It looks like so it's U-shaped.
Good. Which way is it facing?
Down.
Good. So we're a U shape, but we're facing. So what we would call that? Down, down. Awesome. Okay, now pause at this point. Have you observed any patterns yet? How are the first four different from the second four, and what might be the reason for that? Go ahead, Magdalene. Great. Do you guys see what she's saying here? These are all odd. We have 3s, 5s, 7s, and they're going opposite of each other. They're either down, up, or up, down. Whereas the even ones, we have 4, 6, 2. They're going the same. It's either up, up, or down, down. And exactly. So if I'm talking about these ones, I'm going to have the same thing. Now, what determines whether it's facing up or whether it's facing down? Positive or negative leading coefficient. So let's check that. On number 3, what would we expect this to look like? Yeah, we have the 5 here, so it's going to be an S-curve or a flipped S-curve, but what would that negative do? It should flip it. So I would guess that it's going to look like this. And is that what I want to say Isabel? Right? Izzy. Okay, Izzy. Is that what you got? Yeah. How would we describe that? Up, down. Okay. How? How would you do the second one? All right. So what would we use to describe that? Down, down. Okay, tell me your name. What is it? Grimly. What about C? How do we do that? Great. And what do we call that? Up, up. Awesome. Tell me your name. Charlie, what about D? Down, up. All right, great. All right, we're going to formalize that in a minute, but basically what we just saw was if we have an odd exponent, they're going the opposite directions, the start and the beginning, right? And then if it's even, they go the same, and what determines if it's flipped or not? A negative. Now, I'm going to show you a more formal way to write it instead of down, down, or up, up. We'll get to that in just a second, okay? So let's go to this next one. Okay, comparing the graph of a polynomial and its leading terms. So what we have here is a big, ugly-looking graph. Doesn't that just look awful? Now, eventually, you guys are going to learn how to graph that without decimals, but we'll get to there. What I want you to do, though, we're just going to do something interesting here. I want you to graph x cubed, and then I also want you to graph this other one, this ugly-looking one. So on Desmos, start by graphing g of x and f of x. And when you first graph them, they're going to look very different from each other, right? Because one's a parent function, one's been transformed. So let's start by just graphing them and seeing how different they are. Now, if you have any questions, call me over. You need notes, right? Kara, did you have a note? Okay. That's where we're at. And then you need a Chromebook because we're doing decimals. No, we reviewed it. I'll have you turn it into a test. It's not going to be like tomorrow. first graph these, do they look very different? They look like really different, right? But what I want you to do is now I want you to start zooming out on it. And zooming out until they look the exact same. Maybe not the exact same, but basically the exact same. Maybe not that far. Alright, now the point of what I'm trying to get you to see here is when I graph x cubed, it's just going to look like this, right? When I graphed the first one, it was a little bit different. It had like some things going on here, but then it went like that, right? What we're going to be talking about is the end behavior. The end behavior is how it begins and how it ends. What's happening on the right end and on the left end. Now, we don't care about the middles that much. Even though these were pretty different from each other, was their end behaviors different? They're basically the same. They're both, in this case, they're both heading up, right? And on the left, they're both heading down. Now, I'm going to show you how we're going to write that. So let me actually do something right here. So I'm going to make a little graph here. This is my x-axis, and this is my y-axis. And let me actually change that. Instead of y, I'm going to put f of x. Now, let's just talk about x cubed for a quick second, okay? Let's say I'm graphing x cubed. How have we described that end behavior? What would we say that one is? What's it doing on the left? It's going down. What's it doing on the right? It's going up. So we would call this down, up, okay? But what I want to show you is a different way that we're going to write this out that's more mathematically precise, okay? So instead of saying down, because what we're saying here is we're saying on the left side it's going down. What we're going to do is talk about what's called limit notation, okay? In math, a limit is something that we're approaching, that we don't reach. So you guys all took driver's ed, right? You did it? Well, most of you guys have, right? But you know what a speed limit is, right? In an ideal world, would anyone speed? Yes. In an ideal world, there is no speed limit, right? No. Do you guys go the speed limit? Sometimes. What's a safe speeding that you won't get pulled over? About 5. Okay. But technically, with the law, could you get pulled over for going over by 1 mile an hour? Yeah, so what's the limit? What are the safe speeds you can drive and not get pulled over? Let's say you're on the freeway, it's 70. What speeds can you drive? 80? That's pushing it, I don't know, you're risking it there. But let's say the cop was like, I'm going to pull over anyone who's speeding. Basically, you can go anything up to 70, but anything afterwards. Okay, so what we're saying with limits here is what we're approaching, okay? Now, what is the graph approaching? So instead of saying left, we need to say, so as x goes to the left. Well, if I keep going left, 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 what are we approaching? It's just going to get bigger and bigger and bigger, which is what? What do we use to represent something that gets bigger and bigger and bigger and bigger? It's a little symbol, it looks like this. You did say it? Your mask must muffle what you're saying. I can't understand. Okay? So, what we're looking at here is we're going to start looking at, if I'm going to the right, what is x approaching? It's getting bigger and bigger, so it's approaching positive infinity. If we're going to the left, what's x approaching? Negative infinity. Now, that's on the x-axis. On the y-axis, which we're calling f of x, it's the same thing. Will we see the same thing? Yes, the graph goes up. What is it approaching? Positive infinity. And on the bottom, we're going to have negative infinity. So what we have here is we're going to come up with a new way of describing end behavior. It's called a limit notation. So what you're going to do, and I know it's a little weird at first, but you'll get to do is you're going to write the limit, and it's kind of in cursive right there, of f of x. You're always going to write that. So what we're just doing on that is we're going to say, what is it doing? Is it going up or is it going down? But in order to say the left side, we're going to say that x is approaching negative infinity. Because see how on the left side, x is approaching negative infinity. This is just a fancy way of saying, on the left side, our graph is approaching, and then we'll say what it's approaching. Was the graph, was f of x going up or down on the left side? You guys would say it's going down, which means we're approaching negative infinity. Okay, so what we have right here, this is just a fancy way of saying on the left side our graph is going down. But instead what we're going to do is we're going to say the limit of our function as x approaches negative infinity is negative infinity. I'm kind of erasing it to make it look nice. Now, how do we change it if we're on the right side? We're still going to write the limit of f of x. But now instead of x approaching positive infinity, or negative infinity, what is x approaching? Sorry, I just gave you the answer. So now I'm saying, hey, let's go to the right side. I'm going to look and see what is the function doing. Well, it's going up. So that means it's approaching positive infinity. This is basically how we're going to write. On the right side, our function is going up. Now, this is how I'm going to expect you guys to write it on your assignment kind of moving forward. We're not going to get all the way through everything. Okay. But you should be able to get to that. So what we have right here, guys, if you go to this next page, this is kind of showing it. Here are some examples. So this graph, how did we describe this before limit notation? Or the other way around, right? On the left, it's going down, and on the right, it's going up. But do you see how this is just exactly what we just did? The limit of our function as x approaches negative infinity. This is a fancy way of saying on the left side, our graph is going down. On the right side, our graph is going up. I just remembered it. Today in assembly, that means you're probably getting out of here pretty soon. Okay, so let's just quickly formalize this. We'll be done with end behavior here. How is this one different? On the left side, our graph is going up, and on the right side, it's going down. And then do you see what the u's if we scroll over? On the left side, it's going up, and on the right side, it's going up. Left side is going down, right side is going down. I'm going to give you